Are you looking to streamline your application deployment process and ensure consistency across different environments? Docker is the industry standard tool to make that happen. In today's tutorial, I'll guide you through the fundamentals of Docker, from installation to creating and managing containers. Hello everyone, welcome back to another interesting video on Docker tutorial by Edureka. So before we begin, make sure to like, share and subscribe. Do not forget to hit the bell icon to stay updated on the latest tech content from Edureka's YouTube channel. And also check out Edureka's Docker certification training course, the link to which is in the description box below. With that said, let's see the agenda for today's video. Firstly, we will see the Docker use case where IBM Control Desk found its existing solution. Next, why choose Docker and how it can simplify deployment and scaling. Then the prerequisites of Docker like basic OS and command line knowledge. We'll also learn about what is container and how it is used in Docker, having the lightweight app package with dependencies. Moving on to what is Docker, a platform for containerized applications. We will show the difference between the VMs and containers, that is the virtual machines versus containers. Then the Docker components like engine images, containers and Docker Hub. Next, showing about the Docker architecture like client, daemon and also the containers. Then development workflows, which automates coding to deployment steps. Lastly, we will show the hands-on to Docker, like showing the simple installation of Docker and also how to build and run containers yourself. Now let's start with the Docker use case. Imagine that you're working in a fast-paced IT department where issues keep popping up, assets go untracked and changes need approval. That is where IBM Control Desk comes in. It streamlines IT service management by centralizing incident, problem and asset management into one easy-to-use platform. And it helps in solving problems faster with automation and intelligent workflows to improve service quality and keep things running. Let me tell you what is IBM Control Desk. IBM Control Desk is an IT service management tool that helps manage and also support users and IT infrastructure. It builds on IBM Maximo Asset Management, a platform originally designed for managing physical and IT assets. Did you all know that even IBM faced challenges? IBM Control Desk, while a robust IT service management solution, faced several challenges in traditional environments. The deployment process was often complex, requiring extensive configuration and manual efforts that prolonged setup times. Its architecture was resource-intensive, leading to inefficiencies and also higher operational costs. Scalability was another significant hurdle, as adapting to increasing workloads required to major architectural adjustments, limiting its responsiveness to business needs. Additionally, maintenance and upgrade process were frequently causing downtime and increasing operational overhead. And also, the traditional on-premises setup was lagged and flexibility of modern cloud-based solutions, making integration with other tools more difficult and highlighting the need for a more modernized approach, such as containerization to improve performance, scalability, and ease of management. Imagine managing thousands of IT assets and services without scalable infrastructure. This is where the IBM Control Desk was before Docker. So, let's ever think why Docker was introduced into IBM Control Desk. In the IBM Control Desk case study, Docker was introduced to address the challenges associated with managing traditional IT service management applications. IBM Control Desk, a complex and resource-intensive platform, often faced issues with scalability, high resource consumption, and complex deployment process in traditional environments. Docker helped overcome these challenges by containerizing the application components, allowing for more efficient resource use, easier scaling, and simplified deployments. By using Docker, IBM Control Desk could quickly adapt to changes, reduce operational overhead, and also improve performance, aligning with modern DevOps and cloud-native practices. Here is a simplified explanation of the setup described, where a single VM on Red Hat Linux with 2 CPUs and 4 GB RAM hosts both the IBM Control Desk and the DB2 database. Application files are shared via NFS, that is making them accessible to Docker for container deployments. Here comes another step, that is building Docker images. They decided to strictly follow what is stated in the Maximo Asset Management. That is, Maximo Asset Management is a comprehensive software solution developed by IBM that helps organizations manage their assets effectively throughout their lifecycle. That is, it is a part of an IBM Watson IoT, that is Internet of Things, platform, and it's widely used in industries such as manufacturing, utilities, and also transportation and facilities management. A team built a Docker image for IBM Control Desk. like generating the WAR files and also for the UI. Using Dockerfiles, server.xml and also jvm.options, they built images for various applications including UI, cron, MEA, BROS and also API. Since JMS wasn't provided, they created it from scratch. Based on the WebSphere Liberty docs, the service portal image built from the Node.js included certificates for secure communication. Next is that they deployed containers. Containers were deployed on an Ubuntu machine with 4 CPUs and 32 GB RAM. Each application had a container connected to a Docker network for inter-container communication. Docker Compose managed all resources using dockercompose.yml for configuration, including environment variables and host settings. The streamlined approach enhanced scalability, simplified management, and improved integration for IBM control desks. Let me tell you what Docker brought in change. Docker transformed IBM control desk by enabling containerization, improving resource efficiency and scalability. It simplified deployment, reduced downtime, and made updates easier through the component isolation. This enhanced system flexibility, reliability, and overall performance, making IBM control desk more agile and responsive. So, here is a condensed version of 4 points. First is the efficient containerization. Docker improved IBM control desk's resource efficiency and scalability by containerizing its components. They also streamlined deployment, enabled faster setup with fewer errors and reduced downtime. Easier maintenance too. Docker isolated components, which made updates and maintenance more manageable and flexible. Enhanced agility work. Docker was also an enhanced agility that made approach for IBM control desk more agile and responsive to business needs, optimizing operations. Now let's see the overall solution bought. Involving Docker in IBM control desk bought a comprehensive solution by containerizing its application components, which improved resource utilization and scalability. This approach allowed faster and more consistent deployments, reducing setup errors and minimizing downtime. Docker also enabled seamless updates and maintenance by isolating different components, enhancing the system's flexibility and reliability. Furthermore, the streamlined modular architecture simplified operations, reduced operational cost, and increased responsiveness, ultimately transforming IBM Control Desk into a more efficient and agile IT service management platform. Let's see the key benefits bought. First is enhanced scalability. Containerization optimized resource and also simplified scaling as demand grew. Efficient deployment. Docker streamlined deployment, reducing errors and downtime for a more reliable setup. Simplified maintenance. Isolated components enabled easy updates, boosting flexibility and reliability. Last is the cost-effective operations. The modular setup cut costs and also improved responsiveness, making IBM Control Desk more agile. The result bought by this use case was, this article showed a case study using container technology to leverage the native support of WebSphere Liberty profile with the IBM Control Desk product. So, they found that they have more traditional product to container to evolve it toward a cloud-native-like architecture without any need of touch the code. That is, there were also no impact on the application level. This case study showed how container technology was used to transform IBM Control Desk into cloud-native-like architecture without changing the application code. Despite being a traditional product not originally designed by the microservices, containers allowed the IBM to modularize its components, mimicking microservices and improving scalability and flexibility. The process involved identifying dependent modules, that is, by updating build scripts, deploying each module in its own container, setting up communication between them, and testing the setup. This approach shows that even traditional application can be modernized with containers, making deployment easier and more efficient. Now let's see why Docker is so necessary. First, Docker is portable. That is, they run app consistently across any environment. Second, they are lightweight. Containers use fewer resources than VMs, that is, the virtual machines. Then their efficiency, faster setup times and better resource utilization. Next comes the scalability. Easily scale apps using container orchestration. Then is the consistency. Same behavior from development to production. DevOps integration has streamlined CI/CD pipelines. Next is the isolation. Securely run multiple applications on the same host. Last is the simplified dependency management, that is, package all dependencies in one container. Now, let's see the prerequisite to learn Docker. Docker simplifies creating consistent environments across workflows. But to fully harness its power, you'll first need a solid grasp on Linux, command line tools, and also the containerization basics. The three main programming languages needed are Python, JavaScript, and Golang. And the additional prerequisites needed are version control, that is, understanding Git or another version control system can be beneficial for managing code changes in Docker projects. Then is the networking concepts. A basic understanding of networking concepts like IP address, ports, and networking protocols can be helpful for configuring Docker networks. Last is the operating system. Familiarity with command line interfaces like CLI and basic system administration concepts. Next, let's see what is a container. A container technology was launched in 2013 as an open source Docker engine. It leveraged existing computing concepts around containers and specifically in the Linux world. Primitives known as C groups and also namespaces, Docker's technology is unique because it focuses on the requirements of developers and systems operators to separate application dependencies from infrastructure. A container is a lightweight, isolated unit that packages an application and its dependencies. It also ensures it runs consistently across different environments. Now let's see why Docker uses containers. Docker uses containers for its portability as it runs the same anywhere. Then for its efficiency that uses fewer resources than virtual machines. Then comes the scalability, where it can easily scale applications. Last is its consistency, that ensures the app behaves the same in all environments. Now, let's see what is Docker. A Docker is a platform that enables developers to design, develop, and deploy testing to manage applications in isolated, portable environments known as containers. Containers allow you to package an application and all its dependencies like libraries, configurations, etc. into a single unit, ensuring that app runs consistently across different environments. Next, coming to the benefits of Docker. The benefits of Docker are consistency, which runs applications the same way across development, testing, and production. Efficiency, Docker containers use fewer resources than VMs. They also run faster to start and also use less memory and storage. Scalability, Docker is commonly used in cloud environments and microservices architecture, making it easy to scale applications horizontally. Simplified CI/CD, Docker helps automate and streamline continuous integration and continuous deployment pipelines. We will look at the virtual machines versus containers and their differences. The architecture of the virtual machines is that VMs run on a full operating system on a hypervisor, and containers share the host OS kernel but isolate applications. The resource usage of the VMs are heavy, requiring more CPU, memory, and storage as they run separate OS instances. But containers are lightweight and efficient since they share the host OS. The start time of the VMs take minutes to boot, but the containers start in seconds. The portability of VMs are less portable, tied to OS and hypervisor. Containers are highly portable and run consistently across different environments. The performance of VMs have more overhead due to virtualizations, but containers offer near-native performance with minimal overhead. The use cases of the VMs are full isolation, legacy apps, and heavy resource needs. But in containers, we have fast scaling, microservices, cloud-native apps. Containers are ideal for lightweight, scalable deployments, while VMs are better for complete isolation and resource-heavy applications. Moving on to Docker components. The core components of Docker are, first is the Docker engine. This is the heart of a Docker, responsible for building, running, and managing Docker containers. It's available for Windows, Mac OS, and Linux. Docker images. These are the blueprints of containers containing the application code, libraries, and dependencies required to run the application. Last comes the Docker containers. Instances created from Docker images. They are lightweight, isolated environments where applications run. Now let's learn the architecture of Docker. Docker follows a client-server architecture that allows applications to be packed into containers. It consists of several key components working together to manage, build, and run containers efficiently. Here is an overview of Docker's architecture. First, let's learn about the Docker client. A Docker client is a primary interface for users to interact with Docker. Users issue commands like Docker build, Docker run, and Docker pull, while the client translates into API calls that are sent to the Docker daemon. The client can communicate with either the local Docker daemon or the remote one. The key role of a Docker client is they send commands to the Docker daemon using the REST API. Next, let's see about the Docker daemon, or it's also known as the Docker engine. The Docker daemon is the core service running in the background on the host system that manages Docker objects like containers, images, networks, and volumes. The daemon listens to API requests from the client and also handles all the container management tasks such as creating, starting, and stopping containers. It is responsible for executing the container lifecycle, including pulling images, building containers, and ensuring their isolation. The key role for the Docker daemon are it executes commands, managing containers, images, and networks. Next is a Docker image. A Docker image is a read-only template that contains instructions for creating a Docker container. Images include everything needed to run an application, like code, libraries, environment variables, and configuration. The key role of a Docker image is that they are blueprint for creating containers. Docker container. A container is a runnable instance of a Docker image. Containers are lightweight and isolated, but they share the host OS kernels, making them efficient compared to virtual machines. The key role of a Docker container is that they are lightweight, portable, and isolated instance of an application. Next comes the Docker registries, that is a Docker hub. Docker registries are repositories that store Docker image. The most common registry is the Docker hub, a public registry maintained by Docker. Developers can push their custom images to a registry or pull pre-built images for use of their projects. Registries can be public or private, allowing organizations to manage and store their proprietary container images securely. The key role of a Docker registry is that they store and distribute Docker images. Moving on to the Docker Engine REST API. Docker's Engine API allows programmatic interaction with the server Docker daemon. The API can be accessed over HTTP, enabling developers and servers to manage Docker programmatically. All the communication between the Docker client and the daemon happens via the API. The key role of a Docker Engine REST API is that they enable automation and remote management of Docker through the REST interface. Docker Volume. Volumes allow data to persist beyond the lifecycle of a container, providing a way to store and share data between containers or with the host system. They are commonly used to store the database files or other data that are needed to persist even if the container is destroyed or recreated. The key role of a Docker volume is they have the persistent storage for containers. Last comes a Docker network. A network is a group of two or more devices that can communicate with each other either physically or virtually. A Docker network is a virtual network created by Docker to enable communication between Docker containers. If two containers are running on the same host, they can communicate with each other without the need of ports to be exposed to the host machine. They may use the Docker to manage Docker host in any platform manner, regardless to whether they run Windows, Linux, or the combination of two. The key role of a Docker network is to manage communication between containers and external networks. Now let's see the development workflows of Docker. Docker enhances development workflows through, first is a containerization, having packages, application, and dependencies into lightweight, portable containers, ensuring consistency environments across development, testing, and production. Next is the local development. Enables developers to replicate production environment locally, speeding up testing and debugging. Next comes the continuous integration or the continuous deployment, which integrates with CI/CD pipelines for automated build, test, and deployment process. Last is the version control. Supports versioning of images, allowing easy rollback and management of application versions. Now we'll see how to install Docker on our Ubuntu machine. Now let's start with installing Docker on our Ubuntu machine first. Now in order to install Docker on Ubuntu, there are some prerequisites. I would advise you to go to Docker's Install Docker Engine on Ubuntu. Click on the first link that you can see, Install Docker Engine on Ubuntu. Here you can see the documentation and check for all the prerequisites that are specified there. Once you're done with the verification, you can move ahead with the installation process. We'll be using the following: install using the apt repository process to install Docker on our Ubuntu machine. First, open the terminal on your Ubuntu machine. Now let's set up the Docker's apt repository. To do that, first we need to add the Docker's official GPG key. We begin by running a simple apt get update to refresh the package lists. So let's type sudo apt get update. This will refresh all the package list that is needed. Be patient until the packages are getting refreshed. So next we'll install CA certificates and curl on our machine. For that, let's copy and paste the command on our terminal. So as you can see that it's getting installed, type S to continue the installation. CS certificates in our command is a digital certificate that ensures your machine can communicate securely over the internet by verifying the authenticity of websites. The curl is a tool used for transferring data with URLs, allowing us to download files from the internet, such as Docker's GPG key. So now let's move to the next command, that is, we'll be creating the directory for storing the key rings. So for that, let's copy and paste the next command to the terminal. Now let's also add Docker's GPG key to it. We'll download Docker's official GPG key using the following command. Now let's also type the command to ensure that the GPG key can be read by the system. So we'll copy and paste from our documentary and paste it on our terminal. Next, let's add the Docker's repository to APT sources. So for that, we'll add the Docker's repository as the APT sources, and this step will allow Ubuntu to know where to find Docker's packages. So the command we just ran adds the Docker's repository to our APT sources list. This command will specify the architecture of our machine to ensure compatibility. This part will extract the code name of our Ubuntu release, making sure we download the correct version of the Docker. Now, let's also update the package list again. Now that we have added the Docker's repository, we'll run another apt-get update command to refresh the list of available packages from this new source. So as you can see, the reading package list is done. Now we'll install Docker by running the command below. This installs Docker Engine, Docker CLI, and the essential Docker tools on your system. Enter S to continue the installation. So be patient until the Docker's installation is getting installed. In our Docker installation command, we have Docker CE, that means Docker Community Edition, the main Docker engine. And the Docker CLI means the command line interface for Docker. Container.io is the core container runtime for Docker. And the Docker BuildX plugin is a plugin for building Docker images. Docker Compose plugin is a plugin to manage multi-container application. So let's be patient until all the packages in the Docker is getting installed. Finally, we can verify whether Docker was successfully installed by running the Hello World image. So let's type sudo docker run hello world. This command pulls a test image from Docker Hub, runs it inside a container, and displays a confirmation message. If the installation was successful, you should see the Hello from Docker message, indicating everything is working perfectly. There you have it. We have successfully installed Docker on our Ubuntu machine and verified it with the Hello World image. Let's clear the screen. Now that we have successfully installed Docker, let's clear our terminal and explore what happens when we simply type Docker. When you run this command, you will see a list of all available Docker commands. This list is incredibly useful when you're unsure about which command to use. There's also a brief description next to each command that will help you understand its purpose. Now let's go over some of the common commands. First is run. It creates and runs a new container from an image. This is one of the most frequently used commands in Docker. It allows you to run a container based on an image, which can be pulled from a registry or built locally. Next is the execute command. It allows you to execute a command in a running container. This is useful when you need to interact with a running container, such as opening a shell inside it. The ps command, that is the list containers. This command shows you all the containers that are currently running or that have been stopped. Next is the build. This command allows you to create a Docker image from a Docker file, defining the environment and dependencies of your containerized application. Next is pull. It allows you to download an image from a registry. Use this command to pull images from a Docker registry like Docker Hub. Push. It uploads an image to the registry. If you want to share your image with others, you can push it to a public or private registry too. Images. Images are the list of images. This command shows all the Docker images that are available on your local machine. Login. Authenticate to a registry. Use this when you need to log into a Docker registry, for example, Docker Hub, to pull or push images. Logout. This allows you to log out from a registry. This logs you out from the Docker registry too. Search. Search Docker Hub for images. This allows you to search Docker Hub for pre-built images based on your requirements. Next is a version. Show the Docker version information. It provides details about the version of the Docker you're running. Last is the info. It will display system-wide information. This command gives you detailed information about your Docker installation, including how many containers and images are present, your storage driver, and other system-wide stats. Let's start by checking the Docker version. If you're not familiar with the version you're running, you can simply use this command, that is the Docker version. When you're running this command, it displays the current version of the Docker on your system. In case it shows a version 27.3.1, which is the latest version. Similarly, we can check more detailed system-wide information using the info command. So let's type sudo docker info. This info command provides extensive details about your Docker setup, including the number of containers, images, and other resources being used by Docker on your system. So as we progress through this tutorial, we'll dive deeper into many of these commands and understand how to use them in real-world scenarios. Now, moving forward, we'll build a Docker image using Dockerfiles and run that image on your local host as a container on your system. And we'll also open a web browser to see our web page hosted after running the container. So, the first step is to create a directory for our project. We'll use the following command, that is mkdirectory myapp. This creates a directory named myapp. So here you can see that myapp is seen. Next, we'll move into this directory using the cd myapp. Now we'll create a file named index.html. So for that, we'll type the command, that is touchindex.html. Once the file is created, we'll open it using the nano editor and write the content into the file. So I will be typing here, subscribe to Edureka. Then press Ctrl+X followed by Y to save and press enter to confirm the file name as index.html. To verify the content inside index.html, we will use the command, that is cat index.html. So here you can see that subscribe to Edureka is also visible. Our next step is to create a file named Dockerfile. For that, we need to type the command as touch Dockerfile. Then type ls to see. So here you can see that our Dockerfile and index.html is visible. After creating the Docker file, we'll open it in the nano editor and write some instructions into it. So let's type from Nginx. So Nginx is an open source web server that is widely used for serving static content, load balancing, and also acting as a reverse proxy. In this case, we are using it to serve our index.html file. Next, let's type copy index.html /user share nginx/html. So the copy instruction will allow you to copy our index.html file from the current directory into the HTML directory, which is the default directory where Nginx serves its web pages. If your index.html file is in a different folder, you'll need to specify the correct file path in the Docker file. The Docker file is essentially a text file with set of instructions that Docker uses to build an image. So by typing cat Dockerfile, you can see the content that we have written in the nano editor. So next, we'll need to make sure that the Docker is running. If Docker is not running, you can start it with the following command, that is sudo service docker start. If needed, you can also stop the Docker by typing sudo service docker stop. So press Q to exit the status display. As we have stopped the Docker, let's start the Docker again. So let's type the command as sudo service docker start. We can also see the status by writing the command sudo service docker status. So here you can see that a Docker is active and it is running. Now let's proceed to build our Docker image. We'll use the docker build command, that is docker build -t myapp. Let's write the command for the build, that is docker build -t myapp and a dot. Docker build is a command that builds a Docker image based on the instruction provided in the Docker file. And the T flag is used to tag the image with a name. In this case, it is myapp. This makes it easier for reference later. And the dot after myapp refers to the current directory. in which the Docker file is located. So by running the build command, we can see that the error is occurred. So the error shows that the permission denied while trying to connect to the Docker daemon. It means that we need to connect as a super user. So let's type the command as sudo su and then write the command for build. So now you can see that my Docker is getting built. Be patient because it might take time. Now that we've successfully built our image, now it's time to run the Docker. Now let's type the command that is docker run -d -p 6969 :80 my app. -d flag runs the container in detached mode, meaning it runs in the background. And the p flag is used to map ports. In this case, we are mapping port 6969 on a local machine to port 80 inside the container, which is the default HTTP port for Nginx. This command essentially starts a container from my app image, allowing us to access our web page on the local host via port 6969. Now to check the container is running, we use the docker ps command. This will list all the running containers and you should see the my app container running. Finally, to see what we have hosted on the container, open a web browser. Here we'll use Firefox. So on the search bar, let's type localhost 6969. So when you visit to this URL, you should see subscribe to Edureka displayed on the web page, confirming that our Docker container is serving the content successfully. Now, going back to our terminal, now that we have successfully built and run our Docker image locally, let's move ahead and push this image to Docker Hub, where it will be publicly accessible and stored privately in your Docker Hub account. If you don't have a Docker Hub account yet, go to hub.docker.com to create one. It's a simple sign-up process. Once you have created your account, we can proceed with logging into Docker Hub from the Docker CLI. Now, to push our image to Docker Hub, we first need to log in to Docker from the terminal. We can do that using the docker login command. So let's type docker login -u and give our username -p with our password. The U flag is specified for username and the P flag is specified for the password. So once you're logged in successfully, the Docker will display a message confirming the login. Before pushing the image to Docker Hub, we need to tag our local image with a name that includes our Docker Hub username. This ensures that a Docker Hub knows which repository the image belongs to. For that, let's type the command that is docker tag my app, the username, my app : and then the version tag. Here my app : latest is the name and the version tag for the image. We are tagging this image as latest to indicate it's the most recent version. Now we can push our Docker image to Docker Hub using the docker push command. So let's type docker push with the username and the version tag again. This will upload the my app image to your Docker Hub repository. Docker will display the progress as it pushes the image layers. And once it's complete, you will see the confirmation message. So let's be patient unless the image is pushed. So here you can see a confirmation message telling that it is pushed. So after you have pushed the image to the Docker Hub, you can log out of your Docker Hub account from the CLI using the docker logout command. For that, let's type docker logout. This is useful when working on the shared machines or environments where you don't want your credentials to remain stored. To verify that our image is now available on Docker Hub, we can use the docker search command. This command allows you to search the Docker Hub for images. So for that, let's type the command as docker search, username, and my app. So here you can see all the images that we have published. So once the image is on the Docker Hub, we can pull it to any other machine or even to a current machine to ensure that it works as expected. The docker pull command allows us to download the image from the Docker Hub. So let's type the command as docker pull with our username and the image name with the version tag. This command will download the image layers from the Docker Hub to your local machine. So here you can see that our image is pulled successfully. After pulling the image, you can run it on your local machine, just like we did earlier using the Docker run command. So now we can open our web browser and visit, typing the localhost 6969. You should see the same, that is subscribe to Edureka page, confirming that we have successfully pulled and run the Docker image from the Docker Hub. And that's it. You have successfully learned how to push an image to Docker Hub. Search for it, pull it, and run it on your local machine. Now that we have learned how to work with individual containers in Docker, let's introduce Docker Compose. Docker Compose is an essential tool when you're working with multi-container applications. Instead of managing each container individually, Docker Compose lets you define and manage all the services your application needs in a single YAML file called the dockercompose.yml. So here we have the command to install Docker Compose. The option -L makes the curl follow, redirects, ensures that it reaches the final download URL. And the uname-s part dynamically inserts the operating system name, such as Linux or Windows. And the uname -m inserts the system architecture, that is whether it is 64-bit or 32-bit. This ensures the correct version is downloaded for your system. The Docker Compose option specifies the output location where the Docker Compose binary will be saved. In this case, it is user local bin Docker Compose. Once the binary is downloaded, apply executable permissions, that is sudo chmod +x command. To verify that Docker Compose has been installed correctly, let's check the version. So let's type the command as Docker Compose version. So here you can see that the Docker Compose version is v2.29.7. That is the latest version. Now that we have installed Docker Compose, let's create a simple Docker Compose file. This file will define two services, a web server having an image of Nginx and a database that is Redis. So first, we'll create a new directory named Docker Compose file. So let's write the command for it, mkdir Docker Compose file. Then we'll go inside the directory. So type cd Docker Compose file. Inside this directory, we'll create a new file named dockercompose.yml using the touch command. So let's type touch dockercompose.yml. Next, we'll open this file with a nano editor and add the following content. So let's type services, web that uses the Nginx image, and the other file is the database which uses the Redis image. We'll save the file by pressing Ctrl+X, then Y to confirm and save, finally enter to confirm the file name. Before we run the file, let's check if it's valid using Docker Compose config command. This command checks the syntax error or misconfigurations in the YAML file. So let's type the command Docker Compose config. If the file is valid, you will see the content printed out. Now we are ready to run our services. To start both Nginx and Redis containers, we'll use the Docker Compose up command. We'll run it in the detached mode so the containers run in the background. So let's type Docker Compose up -d. So once the containers are up, we can verify by listing the running containers using the docker ps command. You will see two containers running, Nginx and Redis, which were defined in our dockercompose.yml file. Now to stop and remove the containers, we can use the Docker Compose down command. This command will bring down all the services defined in our Docker Compose file. So let's type Docker Compose down. Now let's modify our Docker Compose YAML file to expose a port for Nginx service so we can access it from our browser. So open the file again with nano. We'll add the following lines under the web service to map ports 8080 on our local machine to port 80 in the container. After making this change, let's validate the file again by typing Docker Compose config. If the file is valid, we can now run it again using the Docker Compose up command. If the file is valid, we can now run it again using the Docker Compose up command. Since the Nginx and Redis images are already downloaded, it will skip downloading and simply start the containers. Now let's go to the browser and type localhost 8080. So you'll see a default Nginx welcome page confirming that our container is running and accessible on the port 8080. Once you're done, you can bring down the containers again using Docker Compose down command. Docker Compose comes with several useful commands. To see a list of available commands, we can use the help command. So let's type Docker Compose --help. You will see a list of commands like up, down, config, ps, and many more. These commands allow you to manage your Docker Compose services easily. So, that's a quick introduction to Docker Compose. We have seen how to install Docker Compose, create and validate a Docker Compose.yml file, run multiple containers with a single command, map ports for service access, bring containers down when they are no longer needed. We have come to an end of this Docker tutorial video. If you enjoyed it, please be kind enough to like it. And you can comment on any doubts and queries. We will reply to them as soon as possible. Do look up for more videos and playlists and subscribe to Edureka's YouTube channel to learn more. Thank you for watching and happy learning.